Welcome back to this channel for practice problems for actuarial exams. If you want to find information about me, you can find it at this website, smarturl.it/Jedi. If you would like to find information about the actuarial program that I direct at Illinois State University, it's at smarturl.it/actuary. And if you can and want to support our actuarial students, you can make a tax-deductible donation by going to smarturl.it/ISU actuary donate. Here's a problem from fall 2016 exam MLC. First problem from written answer section. It is an interesting problem because it almost makes you derive the Kolmogorov forward equation. And I've always said or thought that it's unlikely that you would have to derive the Kolmogorov forward equation on an actuarial exam. On the other hand, I have a general warning for you when you study anything for actuarial exams. Anytime this thought goes through your mind, well, they can't possibly ask that on the exam. That probably means it will be on the exam, and you should really go out of your way to study and understand everything. In that something that, oh, you can't imagine they put it on the exam. You should imagine they will put it on the exam. So here you are given the following three-state Markov model. State 0, state 1, and state 2. You see that state 2, you can go into it, but you can't get out of it, so it's absorbing. State 0 and state 1 communicate with each other. You can go from one to the other and back. And for all states I and j, and for all ages x greater than or equal to 0, tpx with superscripts ij is a differentiable function of t, and for I not equal to j, the force of transition from state I to state j at hx is equal to the limit of hpx upper ij over h. That is actually the definition of the force of transition, so nothing unusual here. You should know all that. And here are the questions. Define the symbols tpx and superscript 00 and tpx 00 with a bar above it, and explain why these two probabilities are not equal for this model. So in the superscript, it tells you what state you go from to, 0 and 0, so you go from 0 to 0. And if there is a bar above it, that means that you go from 0 to 0, so you're really in 0 state, and you never leave it. The bar indicates that you are continuously in state 0 throughout the time from hx to hx plus t. We'll say it again in a moment. I just want you to be familiar with the notation because it's important. And then the probability t plus hp x 00 can be expressed as t plus hp x 00 equals tpx 00 times hp x plus t 00 plus tpx 01 times hp x plus t 10. So it's not a 10, it's 10. That's what it indicates. Use this equation to derive the Kolmogorov forward equation for tpx 00. Okay, so one thought that should come to your mind is the Kolmogorov forward equation is a differential equation for the probability of survival. So you'll be taking a derivative with respect to t of this expression that you see here, and you need to find the equation that describes it. Prove that, derive that equation based on what you see here. So obviously what you're going to do is you'll try to find the derivative of tpx 00 with respect to t using the equation that you see, but then you notice that there's t plus h there. So if you subtracted tpx, so t plus hpx 00, if you subtracted from it tpx00 and divide the whole thing by h. That's a difference quotient for the derivative you would be working with, and the limit of that is the derivative. It's just a comment. It's an important thing to note in this. You are also given that the force of transition from 0 to 1 at h x plus t, instantaneous force of transition, is 0.5 for all t, so it's constant force. And mu x plus t 0 2, transition from state 0 to state 2, is kt for all t, so it increases, assuming k is positive, but of course it is, because it's a force here. So this is increasing with respect to t. And then 2-year probability of survival in state 0 continuously for life hx is 0.165. Based on this information, you're supposed to calculate k. So tpx00 is the probability that a life who is currently hx and is in state 0 is also in state 0 in t years at hx plus t. tpx00 with a bar above it is the probability that a life who is currently hx and in state 0 is also in state 0 throughout the following t years, continuously all the time. In general, these probabilities are the same only if after leaving state 0 a life cannot return to state 0. In this model, the probabilities tpx00 and tpx00 with a bar are not the same because transitions in both directions between state 1 and state 0 are possible. We noted that when we look at the graph. So the first probability, tpx00, includes the possibility that x leaves state 0 and then returns to it in the period 0t, while tpx00 with a bar above it does not. So let's, for part B now, let's note that starting from state 0 at hx, a person can be either in state 0 or in state 1 at hx plus t, and still end up in state 0 at the end. Because the person could also go to state 2, but that's it. The person will never return to state 0. So if we're looking for the probability that life hx starts out at state 0 and is in state 0 at time t plus h, that person can only either be in state 0 and then in state 0, or can go to from state 0 to state 1 and then back to state 0. Now, the number of these transitions, there could be a lot of them. We're not restricted in any way. Nevertheless, if we look at a specific point in time, at hx plus t plus h, then at that time being in state 0, in relation to where the person is at the beginning, which we know is 0, state 0, and where the person is at time t, which could only be either state 0 or 1. If the person goes to state 2, that person will not return to state 0 at time t plus h. So for 0 at time t plus h to happen, at time t the person can be either in state 0 or in state 1. That means, this is basically a law of total probability statement, that t plus h px00 is equal to tpx 00 times hp x plus t00 plus tpx01 times hp x plus t10. Okay. This means that we can also write this hp x plus t00 as 1 minus hp x plus t01 minus hp x plus t02, and get this expression, and then take this tpx00 multiplied by 1 to the other side to get something like a difference quotient, and leave everything on the right hand side. Now if we divide it by h, then it's a difference quotient, so the limit of it as h goes to 0 will be the derivative that we want to resolve. But that means we have to divide both sides by h, because we divided the left-hand side. So we divide the right-hand side. And when we divide those probabilities of surviving for h years from x plus t, and that thing is divided by so hp x plus t01 plus hp x plus t02, both divided by h. And when we divide hp x plus t10 by h, then the limits of those are forces of transition. So what we get is that the derivative of tpx00 is minus tpx00 times the sum of all forces of transition that take a person out of state 0. What do we call that sum? We call it the total force of transition out of state 0, and it's denoted by mu x plus t upper 0. So we end up with the equation, the derivative of tpx00 with respect to t is equal to minus tpx00 times mu x plus t upper 0 plus tpx01 times mu x plus t10. And this is actually the Kolmogorov forward equation we're supposed to derive. So this is a complete answer for the question asked on the test. But because this Kolmogorov forward equation is always on the exam MLC and it's important, I would like to point out to you that the book does not derive the matrix form of Kolmogorov forward equation, and it is so hard to memorize it in the algebraic form that they give it to you. So I would like to show you what the matrix form of Kolmogorov forward equation is, and it is the derivative with respect to t of tpx is equal to tpx times qx plus t, where this tpx is, of course, the standard transition matrix. So on the left-hand side, we have its derivative, and on the right-hand side, the standard transition matrix multiplied by what is called the generator matrix, which consists of the forces of transition, except along the diagonal, it doesn't have the force of transition from 0 to 0. It actually has minus the total force of transition out of the state 0, so that the sum of all the terms in each column, in each row of this generator matrix is always 0. And in this case, by the way, we know that the forces of transition out of state 2, which is absorbing death, there is no coming back from it, so there is no force for coming out of it. So all the entries in the last row of this generator matrix are 0. And this transition matrix, for which we also have some 0 probabilities, because in certain direction transitions do not happen, specifically from state 1 to state 2, and from state 2 to state 0, and from state 2 to state 1. So given this, we know what the form of the Kolmogorov forward equation in matrix form is. We can write it out now. So this is the form of the matrix equation that we get. We take all these derivatives and we multiply the two matrices, and so that tells you, for example, that if you take the first column, first row entry, this d over dt tpx00, that's going to be equal to the dot product of the first row and the first column in the second pair of matrices, so the right-hand side pair of matrices. And you do that for every entry. And that's how you get all possible Kolmogorov forward equation for all of the parameters in the transition matrix. So this is specifically what you get, and of course the very first one, first row, first column, is the equation considered in this problem, and all the other ones are the other possibilities. And also it's interesting to note that only 6 of these equations are meaningful, and 3 are meaningless. 6 are actual equations, 3 are meaningless because there's 0 identities. 0 equals 0. For part C, we have that 0.165 is equal to 2px00 with a bar above it. Well, that probability is the probability that a person is in state 0 at the beginning and remains continuously in that state, which means that the force of transition out of the state never took it out. So the person survived that force. And this is like doing the calculations of survival with a constant force in regular life contingencies. You know that the probability of survival of t years and the constant force would be e to the minus mu t. Well, it's not constant force exactly, but it's always e to the minus the integral from 0 to whatever time we're looking at. The force out of the state, so in this case it's mu01 plus mu02 because we're talking about state 0. So the integral from that, in this case from 0 to 2 dt. The sum of the forces is 0.5 plus kt, so we need to take the integral of that expression, which will be, well, 0.5 is a constant, so that's no problem, and then kt, k is a constant we know, so it will be 1/2 t squared, and we evaluate it from 0 to 2, and we end up with e to the minus 1 plus 2k. So the natural logarithm of 0.165 is equal to minus 1 plus 2k, because when you have an equation in which the unknown, in this case k, is in the exponent, you should start solving it by taking the natural logarithm of both sides. So ln of 0.165 is the left-hand side natural logarithm, and then the natural logarithm of e to the minus 1 plus 2k is just minus 1 plus 2k. We solve it for k, and it ends up being minus ln of 0.165 minus 1 divided by 2. No, these minuses don't mess up anything. Ln of 0.165 is the natural logarithm of a fraction, which is going to be negative, and then minus sign in front of it will make it into a positive number, and we end up with about 0.4 approximately for the value of k. And that's the end of this problem. Please remember that this is copyrighted material, and also the problem comes from a past Society of Actuaries examination, so the problem itself belongs to the Society of Actuaries. Good luck in your studies and good luck on the test.